All right, welcome back to The Explainer. Today, we're going to dive into one of the most, truly fundamental ideas in all of computer science, the linked list. And what's so cool about it is that it's this really elegant, really powerful concept, but it's also kind of hiding in plain sight, powering all sorts of tech you use every single day.
So let's just jump right in with a question. Think about this for a second. What could a music playlist and your browser's back button possibly have in common? One's for your favorite songs, the other's for navigating the web. On the surface, they seem completely unrelated, right?
Well, it turns out the secret sauce connecting them is this beautifully simple idea that really changed how we organize data. It's all about this incredibly flexible, super powerful way to just chain pieces of information together, one after the other.
Okay, so to really appreciate why linked lists are such a game changer, we first have to understand the problem they were built to solve. We need to look at what came before, and that story, well, it starts with the good old arrays. Now, look, arrays are great for some things. You can think of them like a row of mailboxes, right? They're all in order. It's super fast to grab something if you know its box number. But, and this is a big but, they have some major drawbacks. They are so rigid. Once you set the size, that's it. You're stuck. And what if you want to add something new right in the middle? Oh man, it's a total pain. You have to physically shift every single element after it down the line. Deleting something, same nightmare, just in reverse. It's clunky, it's inefficient, and you can end up wasting a ton of memory.
So that's the big question, right? How do we get that nice, predictable order of an array, but with a ton more flexibility? Well, this is where our hero of the day, the linked list, makes its grand entrance.
Okay, so the absolute heart of a linked list is this thing called a node. Just picture a little container, and it has two jobs. First, it holds your actual data. You know, a number, a name, a song title, whatever. But the second part, this is the real magic. It holds a pointer. And a pointer is really just an arrow, a signpost, that tells you the exact memory address of the next node in the sequence.
And right there, that's the huge difference. With an array, all the elements have to live right next to each other in memory, like houses on a street. But with a linked list, the nodes can be scattered all over the place. It doesn't matter. The only thing that ties them together and creates that order is that chain of pointers. It's a list connected by its links, not by its physical location.
All right, so now that we've got the basic idea down, let's check out the different flavors of linked lists, because each one is just a clever little twist on that core concept designed to tackle a specific kind of problem.
So first up, we've got the most basic version, the singly linked list. The best way to think about this is like a one-way street, or maybe a scavenger hunt. Each clue, each node, tells you where to go next, but you can't go backwards. You can only move in one direction, forward.
And this is where you really start to see the power. Remember that pain of trying to add something to the beginning of an array? Well, check this out. With a linked list, adding a new item to the front is ridiculously easy. Seriously, you just make your new node, you tell its pointer to aim at what used to be the first item, and then you just say, hey, you're the new head of the list. That's it. 3 simple steps. It's crazy fast, super simple, and there is absolutely zero shifting involved.
But, that one-way street has an obvious downside. What happens when you actually need to go backwards? Well, that's where the doubly linked list comes into play. And the idea is so brilliant in its simplicity. You just add a second pointer to every single node. So now each node doesn't just know what's next, it also knows what came right before it. And that one simple change, it turns our one-way street into a full-blown two-way highway. All of a sudden, you can travel in both directions. And hey, remember that question from the beginning? This is exactly how your browser's back and forward buttons work. It's how undo and redo works in your text editor. Every page you visit or every change you make is a node in a chain, and you can just move back and forth along that chain.
Okay, so our next type asks a really interesting question. What if the list just never ended? What if, when you got to the last item, it just looped right back to the beginning? For that kind of problem, we have the circular linked list.
So with a circular list, the very last node doesn't point to nothing. There's no end of the line. Instead, its next pointer links all the way back to the very first node. It creates this perfect, continuous loop. And this is ideal for any kind of task that needs to just keep repeating in a cycle, like how a computer's CPU gives a little slice of processing time to each running program over and over and over again. That's a classic example.
All right, so we've covered the main types, but let's take it a step further. What if a list could actually get smarter the more you used it? Let's check out a more advanced concept that does exactly that.
This is what's called a self-organizing list, or SOL. And honestly, it's pretty much what it sounds like. It's a list that pays attention to how you use it and then rearranges itself to be more efficient. The whole idea is, look, if you keep asking for the same item over and over, shouldn't the list make that item easier to find next time? So it does. It automatically reorders itself, bumping the most frequently accessed stuff right up to the front.
And there are a couple of cool strategies for this. The most aggressive one is move to front. You touch an item and bam, it immediately jumps to the head of the list. Transpose is a little more chill. When you access an item, it just swaps places with the one right before it, kind of slowly bubbling its way up to the top over time. And then there's the count method, which is basically a popularity contest. The list literally keeps a running tally of how many times you've accessed each item and then sorts the whole thing based on that score.
Okay, so we've definitely covered a lot of ground. Let's take a step back and really nail down the so what. Why does all of this matter? Why are linked lists so crucial to understand?
This really puts it all into perspective. It's all about picking the right tool for the job, you know? You have to ask yourself, is my data static and I just need super fast access by index? Then yeah, an array is probably your best bet. Do I need a list that's dynamic, that can grow and shrink really easily? A singly linked list is perfect. Do I need to go both forwards and backwards, like with browser history? That's a job for the doubly linked list, no question. And for anything that needs to repeat endlessly, the circular linked list is designed for exactly that.
You know, it really all comes down to the simple but powerful quote from one of our sources. It just says, linked lists overcome the limitations of arrays. A linked list can grow or shrink dynamically during its lifetime, and that second part is everything. That ability to grow or shrink dynamically, that is the revolution. It's about freedom. It's about flexibility.
So when you boil it all down, it's such an elegant idea, isn't it? Just data plus a link to the next piece of data. But from that simple building block, we've seen how you can solve some really complex problems. So I want to leave you with this final thought. Just for a minute, forget about the code. Think bigger. What problem, maybe in your work or your life, could you solve by taking separate things and just linking them together in a brand new way?